Hi, it's the third part of section 1.6. In the first part, we defined inverse functions, and in the second part, we introduced the logarithmic functions as the inverse of exponential functions. Now, in this part, we'll study inverse trigonometric functions. Trigonometric functions are periodic, so they are not one-to-one. However, if we restrict their domains, then they'll become one-to-one. So we can define their inverses. Let's see these figures. Now sine y equals sine x will be periodic here. But if we restrict the domain from minus pi over 2 to pi over 2, then it becomes an increasing function. Same way, if we restrict the domain from 0 to pi for cosine x, then it is a decreasing function. For tangent, and from minus pi over 2 to pi over 2, excluding boundaries. Now, in this region, tangent x is increasing function. Its reciprocal cotangent will be decreasing function from 0 to pi. And reciprocal of cosine, which is a sec x. Now, if we consider from 0 to pi, then although the value here is not, the function is not defined at the point pi over 2, also it has two pieces. As from half it is increasing, and another half it is go down to minus infinity and increasing. In this way, it is defined. But if you are using the horizontal lines, then in the domain, the horizontal lines will meet only once to the graph, so that it is one-to-one. So you can define its inverse. The reciprocal of sine, which is cosecant, for that function, if we consider from minus pi over 2 to pi over 2, then again it is one-to-one. Even though again you have two pieces, and here in range also we have such gap. With these restrictions of the domain, they are one-to-one, so that we can define inverse. So yeah, to find the inverse here, we have to solve for x. So for example, right now for sine x, and to find its inverse, we have to find y equals sine x, start with y equals sine x, and we have to solve for x. So that is, okay, this is not a function of having addition, subtraction, multiplication, division, so that we introduce a notation for that, solving for x, so that now, and from this one, we introduce here now the name arc sine. Okay, you can use this one as a small letter, but anyway, arc sine y. That is, with the introduction of arc sine, we solved it for x, and now extend x and y, so that y is the same as now arc sine and x. So we recheck that one. Okay. So along with the arc in front of a sine, we consider that once arc appeared, then it is inverse function of a sine. Sometimes, okay, symbolically we say that in here x equal now sine inverse of y, so that rather than here arcsine, sometimes you will see here that is a sine inverse of x. Either way, arcsine or sine inverse, either way we'll try to express the inverse of sine function. Now here, as for earlier the part, when we introduced the logarithmic functions, the domain, okay, for exponential function, and domain of exponential function becomes now range of logarithmic function, and now range of exponential function becomes the domain of logarithmic functions. The same way here, for that restricted function sine x, now domain is minus pi over 2 to pi over 2. Now range is minus 1 to 1. So that is here opposite for arcsine. So domain is minus 1 to 1, and range is minus pi over 2 to pi over 2. For every here, for 6 functions, we define the inverse of these trigonometric functions, and exactly the same principle will be applied. So exactly the same way they are defined. Okay, here now here in definition, here we say that y equals sine x is the number in minus pi over 2 to pi over 2. That means that range is given in this way, and here y equals arcsine is defined like over there, so that here, and now solve for, okay, for this one, solve for y will reach at that one. For solve for x will reach at that one. So in this way, it is defined. That is exactly same way for the definition of logarithmic functions as the inverse of exponential functions. Now for y equal arc cosine x, also the same, so that here that is inverse of cosine function. Okay, let's go to this example. Let's see, try to evaluate here arcsine square root of 3 over 2. Okay, now if you say this is, for example, y or t, x, it doesn't matter. You can choose any letter. Okay, let's say this is y. Then it is the same as, from the definition, the same as now sine y equal square root of 3 over 2. Right? Okay, so that is and so that you can easily see that here from this one here now y must be what is that? So that is shape coming from that one, 2, 1, and square root of 3. That angle is y right now. So this is same as pi over 3. Okay. So that is a value, and here the output of arcsine will be angle. Here sine function is getting angle, producing a number, so that eventually arcsine will produce angle. Okay, so for arc cosine, again the same. This time we'll try to get, okay, we'll use this one in this t. It doesn't matter. You can use again y, but we are using t. Then that is same as now cosine t equal minus 1/2. Right? Okay. And so that when we define the cosine, the arc cosine, in fact, now that is from it's from 0 to pi, so that your t must be between 0 to pi. But anyway, here now is minus 1/2, so that if you use here circle of radius 1, now cosine is horizontal component, so it's a minus half is here, so that's minus half, and now the angle from here to there, right? That is exactly now angle T. So you can easily figure out that that is here, here T is 2 pi over 3, okay? Okay, now we'll go to here this example. Okay, is it correct? And sine and arc sine, can we cancel these two? No. And the reason is, in the beginning, an arcsine, let's go to the definition. Arcsine, the range must be from minus pi over 2 to pi over 2. This arcsine is defined from that restriction for the sine function, so that arcsine must be, the output must be between minus pi over 2 to pi over 2. Okay. So here, okay, anyway, for that one, here the output of arcsine is now out of the so that means that it's not in here minus pi over 2 to pi over 2. So it is wrong. Then the correct one can be found in this way. In fact, the inside of this parenthesis and 9 pi over 4, okay, here, let's say here now, 9 pi over 4 is the same as 2 pi plus pi over 4. So that this inside the parenthesis is the same as a sine, now pi over 4. So that, and after application of sine and its inverse, so that eventually that must be here pi over 4. So that if it is pi over 4, then it is correct. Okay. Now for that one, and you so that to answer for this part, you may hesitate, but it's not correct. The reason is arc cosine cannot get value 2, because arc cosine will take a value between minus 1 to 1. Okay, let's go back to the picture. Here, arc cosine is now defined from minus 1 to 1, and values from 0 to, ranges from 0 to pi. Okay, we have here. So it cannot take here 2. Also, here the cosine cannot make a value larger than 1. Then output of cosine must be also minus 1 to 1. So it's wrong. There's no way to correct it. Okay. Okay, now this official definition for tangent x, cotangent x, and sec x and cosec x and their inverses. So already I explained over there. Okay. And the manner of defining an arctangent, arccotangent, arcsecant, arccosecant are exactly the same as for inverses of cosine and sine. Okay, let's try to find the exact value for these expressions. Okay, now for this one, let's say this is x. Then it's the same as now cosine x equal minus 1. Okay, cosine x minus 1, and here op of inverse cosine must be between 0 and pi, so that we know that once here now x equal pi, then here cosine x is -1. So if you are using, for example, circle of radius 1, now here -1 is that one, so angle is from here to there, that one, so that is pi now. You can see that. Now, okay, again, if we are putting this one as x, then it's the same as now tangent of x equal -1, and slope -1 is possible when x equal minus pi over 4. Quite easily you can get it. Now, that is a sine and arcsine. They are inverse each other. If this value is inside the domain of that arcsine, then you can cancel out. Is it inside? Yeah, arcsine is admitting the values from here -1 to 1, and this value is between -1 to 1, so that now simply you can cancel out, so that the value is 1 over square root of 2. But be careful, earlier, like over there, this one, okay, this value is inside, but here that one is basically, it is producing value and between here minus pi over 2 to pi over 2, so it's not inside the range. And okay, and also the value over there is inside range of sine x, so that no problem for canceling out. Okay, here we simplify the expression cosine and tangent inverse of x. So we'll do the step by step for this term. Let's start with that inside this parenthesis. Let's say tangent inverse of x is y. We introduce another variable y. Then, and inverse tangent function has range minus pi over 2 to pi over 2. And from definition, this equality is the same as now tangent y equal x. Here, once you did this, then what we have to find is cosine y. We write down this one as y. So what we have to get is cosine y. And what we know, what we introduced is now tangent y equal x. So that cosine, here now cosine, tangent should be now related. They are related. So we have to use some formula involving cosine and tangent. One of the formula is, okay, that is sec is basically 1 over cosine. So there is a sec squared y equal 1 plus tangent squared. Now tangent y is the same as here x, so that this term can be written as 1 plus x squared. And here now and y is now between minus pi over 2 or pi over 2, so that basically the cosine in this region is positive. So sec is positive, which means that if you are taking square root, then now here, rather than minus, plus minus, we are choosing positive here. So the sec y is just simply positive square root of 1 plus x squared. Okay. So here, now the target we have to get is cosine y. So we take reciprocal. So we recheck that is 1 over square root of x squared plus 1. So that's the final answer. Now, this manipulation, algebraic manipulation, seems quite complicated. But by using geometric manipulation, you can do it much better way. Let's try to simplify this expression. Now, this is sine tangent inverse of x. Okay. Now, after doing this one, again, we go back that problem and we'll try to do it much better way. Okay. The same way for that one, let's try to introduce y for this term. Then, and here we can say that this tangent y equal x. This is angle. This is now the slope. So let's try to make a geometric expression for that one. If you start with a right triangle, okay, like that, okay, then angle will be y, and here the x means that the tangent y is this side opposite and over that adjacent, so that means that once it is 1, then it must be x. If you set up in this way, then that is exactly tangent y is here x over 1, so which is x, right? Okay, now for this one, what you have to find is that y is already geometrically expressed, so that, and what you have to do is now sine y. Okay, sine y, but sine y is here opposite over hypotenuse. So we have to find this hypotenuse. But that triangle is right triangle, so that by using Pythagorean theorem, we can say this hypotenuse length is the same as x squared, square root of x squared plus 1. And this squared, this side squared plus that squared will be that squared. That is Pythagorean theorem. So there. Now, sine x, quite simple. Now, x over square root of x squared plus 1. So that is the final answer. Now, go back to the earlier problem. This is exactly here now. The same over there. Tangent inverse x is, now we set it y, but now for the early example, we try to get cosine tangent inverse x. So that is the same geometric expression, and then cosine of y equal, now cosine y is a ratio between here, that one and that one. So that same is here 1 over square root of x squared plus 1, which is exactly same as that. So now that algebraic expression is complicated. However, if you understand the geometric manipulation, then you can do it much simpler. Okay, that's the end of the section and end of the chapter. Thank you.